All right, we're about to dive into a scientific idea that is so out there, it could completely reshape how we see everything. It's called the quantum ethics hypothesis. And the core idea is that your sense of right and wrong, it isn't just in your head. It might just be part of the universe itself.
So let's just start with the central question, because it really is a mind bender. What if every single time you make a tough moral call, you're not just wrestling with your conscience? What if you're actively taking part in the construction of physical reality? It sounds like science fiction, I know, but just hang with me.
You know, for centuries, we've pretty much agreed that morality comes from culture or psychology or just the complicated firing of neurons in our brains. This hypothesis, though, it suggests we've been looking in the wrong place entirely. It says we need to look past the usual brain chemistry and go much, much smaller, into the quantum world. Okay, so here's the absolute core of the quantum ethics hypothesis, or QEH for short. It says a moral choice isn't just some abstract thought. No, it's a physical event that literally helps build our world. You know how at the quantum level, reality is often described as this cloud of possibilities? Well, the QEH suggests that our moral decisions are part of what causes that fuzzy cloud to collapse into the one solid reality we all experience. It's a pretty wild idea. And if you think about it, this is a massive shift. I mean, it takes the study of ethics, something that has always lived in the world of philosophy and psychology, and suggests it might actually belong in an experimental physics lab. It's arguing that morality has a physical signature, something we might actually be able to detect and measure. That all sounds incredible, but it immediately brings up a huge question. How? How could the human brain, this warm, wet, messy biological machine, possibly be doing quantum mechanics? It seems impossible. To even begin to answer that, we have to look at the proposed engine for how this would all work. The QEH doesn't just appear out of thin air. It's actually built on top of an already existing and, let's be clear, very controversial theory of consciousness called orchestrated objective reduction, or ORC-OR. This was developed by giants like Sir Roger Penrose and Stuart Hameroff, and it proposes that consciousness isn't just something that happens when a brain gets complex enough. Instead, it originates from real quantum processes happening inside our neurons. So where exactly is this quantum computation supposed to be happening? Well, the ORC-OR theory points to a really surprising place. Not in the synapses, the gaps between neurons, but deep inside the neurons themselves, in these tiny protein tubes called microtubules. The idea is that these are the brain's quantum bits, its qubits. Then other structures called gap junctions could link these quantum states across millions of neurons, creating this huge, coherent field of, well, conscious moral intention. But, and this is a really, really big but, this entire idea runs straight into a massive scientific wall. It's a problem that has challenged every single quantum theory of consciousness, and it's called decoherence.
Okay, so a quantum state is incredibly delicate. The tiniest interaction with the world around it can just shatter it. That's decoherence. And critics, pretty fairly, point out that the brain is probably the worst possible place for quantum effects. It's warm, it's wet, it's electrically noisy. It's just a chaotic environment. So how could any fragile quantum state possibly survive in there?
And this is where the real scientific debate is raging. On one side, you've got physicist Max Tegmark, who famously calculated that any quantum state in the brain would dissolve almost instantly, way too fast to be useful for thinking. But proponents like Hameroff argue back. They say the brain isn't just some passive soup. It's an active system that might be using energy to shield these delicate states, protecting them from the noise just long enough for a conscious moment to happen.
This is a fascinating debate, for sure. But without any hard evidence, it's just talk. So the researchers behind QEH have proposed this really ambitious three-phase experiment, kind of like a scientific gauntlet, to try and prove their hypothesis one way or the other. The plan has three big steps. First, they just want to find a correlation. They want to put two people in a situation where they have to face a moral dilemma together and use advanced scanners to look for some kind of weird quantum-like synchronization between their brains that classical physics just can't explain. Second, they'll test for causation. Here, they try to use something like weak magnetic fields to see if they can ever so slightly nudge a person's moral behavior by influencing quantum states. And the final, most direct test is manipulation. Using some amazing technology called optogenetics, they try to turn the quantum processes in neurons on and off like a light switch and see if it only affects moral reasoning, leaving everything else untouched.
And what this all shows is that these aren't just vague philosophical musings. The hypothesis makes real, concrete, testable predictions. For example, They're predicting that a moral intention should create a very specific quantum signature, a super classical spike in coherence that they think they can actually pick up with advanced brain scanners. By making specific predictions like this, the QEH moves out of pure speculation and into the world of real, honest-to-goodness science, even if it is incredibly ambitious.
So let's just take a step back for a minute. This is definitely high-risk research, and it could easily turn out to be a dead end. But what if it isn't? What if they're right? What would it actually mean if the quantum ethics hypothesis were proven to be true? This quote from the original research paper really just gets right to the heart of it. If QEO is true, then our sense of right and wrong isn't just something we made up. It's not a product of our evolution or our culture. It would be a fundamental, baked-in part of the cosmos, as real as gravity or the speed of light.
The implications are just staggering. All of a sudden, free will isn't just a philosophical debate, it's a real physical process we can study. Our personal responsibility for our choices would suddenly have cosmic significance. And two fields of study that we've always kept completely separate, physics and ethics, would suddenly be woven together, fundamentally entangled.
Which leaves us with a final, really profound question to think about. If our deepest moral struggles aren't just happening inside our own heads, but are actually part of a process that's woven into the very fabric of reality, how does that change our place in the universe? What does that mean for how we choose to live our lives?
Okay, let's unpack this. For decades, right, we've tried to understand consciousness by thinking of the brain as this super sophisticated computer. And we look at the wiring, the firing rates, the complex classical algorithms running our thoughts. But what if the really deep questions like where free will, where morality actually comes from, what if they need a totally different rule book? What if the answers are somehow written into the very geometry of space-time?
That's exactly the idea behind the material we're looking at today. We are really digging into the quantum ethics hypothesis, or QEH for short. And yeah, it's inherently radical, definitely a high-risk, high-reward kind of approach. It's trying to bridge this huge gap between physics and moral philosophy.
And it's quite a bridge it's trying to build. Massive, really. QEH goes way beyond the usual classical models, the ones that say ethics is just something that emerges from complex brain wiring, or maybe it's just cultural conditioning. The core idea here, the really striking part, is that conscious, intentional, moral decision-making is fundamental. It's a physical process rooted in quantum mechanics, not just some calculation running on the hardware. It suggests our deepest ethical choices are actually involved in constructing reality as we observe it.
That's right. For you listening, the paradigm shift is, well, it's profound. If you usually think of ethics as soft, philosophy, sociology, psychology, QEH forces you to see a genuine ethical choice, that commitment to a moral path, as a hard physical event. So our mission today is to trace this incredible idea. We'll start with its theoretical roots in quantum consciousness, and then crucially, we'll walk through the three very distinct, very ambitious experimental phases they've proposed to actually test it.
Okay, let's start right at the core. The engine of the hypothesis. What is a moral choice, physically speaking, according to QEH?
So the central idea is that an intentional moral choice acts like an objective quantum measurement. Think about when you face a real ethical dilemma, a conflict where the outcome isn't just calculation, maybe deciding between costly altruism versus self-gain. QEH proposes that this conscious act, this commitment, this resolution, actually triggers a non-computable wave function collapse. Specifically what they call an orchestrated objective reduction, or an OR event.
Hold on, so the conscious experience of resolving the dilemma, that's the collapse. It's not just happening alongside it, it is the physical collapse itself.
That's the essence of the claim, yes. This intentional act is proposed to transiently select a specific measurable state of quantum coherence. And this state is aligned with a particular ethical, valent selfishness, maybe, or deep altruism. The theory suggests this process imprints a kind of temporary ethical order onto the brain's quantum field. And here's the really key prediction for experiments. If this is right, that resulting coherent state should have measurable signatures, signatures that actually violate the known rules of classical statistics.
Ah, okay. Violating classical bounds. That's the smoking gun, then. That tells you it's definitely not classical computation. It's something genuinely quantum entanglement, maybe, or superposition, something your standard computer just couldn't replicate. And this is where physics and philosophy really collide, isn't it? No more separation.
Exactly. Historically, we kept them in separate boxes. Physical laws over here, human morality over there, irrelevant to each other. QEH says, no, they have to be unified. It implies consciousness and ethics are actually co-creating the world we observe. It suggests there's this entangled layer of reality where our moral landscape and the physical universe are fundamentally linked.
Okay, that sounds absolutely mind-bending, but we need to ground it. Where could this quantum stuff even be happening? I mean, the brain is warm, it's wet, it's noisy. Seems like the worst place for delicate quantum states. So to really get QEH, we have to start with its foundation, right? This orchestrated objective reduction framework, ORCH or R.
Yes, ORCH-OR. It was developed famously by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff. And it suggests consciousness doesn't just bubble up from neurons firing classically at the synapses. That's the standard view. Instead, ORCH-OR puts the origin of consciousness deeper, at the quantum level, inside the neurons themselves.
Inside the neurons. Okay, so what's the physical hardware for that? What's doing the quantum work?
The theory points to neural microtubules, MTs. These are really important structures inside all our cells. Now, classically, we know microtubules act like the cell scaffolding. They give it shape, help things move around, basic cell biology. But ORCH-OR proposes that because of their structure, this incredibly ordered, almost crystalline lattice of proteins, they can actually function as quantum information processors. Essentially, they act like biological qubits.
Qubits inside microtubules, that's a huge claim. Why them specifically? Why not, I don't know, mitochondria or something else?
It really comes down to their structure. Microtubules are made of these protein dimers, alpha and beta tubulin, arranged in a very precise helical pattern. This regular arrangement, along with subtle changes in the electrical states of those proteins, theoretically allows for complex quantum superpositions to form and maybe even communicate along the lattice. It's this unique, ordered environment that's thought to allow for the kind of non-computable quantum processing needed for genuine choice, linking that choice, as Penrose suggests, right down to the fundamental geometry of spacetime.
But okay, a single microtubule is tiny. For a big, brain-wide, moral decision, deciding to risk your life for someone, that quantum state would need to cover a huge area, right? A collapse in just one MT wouldn't do much. How does the theory scale this up? How does it get coherence across large parts of the brain?
That's a critical question, and it's something Hameroff specifically addressed. The proposed mechanism for scaling up involves gap junctions. These are basically direct electrical connections between the cytoplasm of adjacent cells, neurons, even glial cells. They allow for superfast signaling. In the QEH context, the idea is they also act as conduits for quantum coherence, linking the MTs in different cells together.
So the gap junction isn't just passing electrical signals, it's acting like a quantum bridge, a tunnel.
Precisely. They're thought to be small enough to allow quantum phenomena, maybe electrons, maybe some kind of charge density, wave to tunnel across. This could sustain quantum coherence beyond just one cell. And this mechanism is proposed to allow for large-scale coordinated quantum activity across wide areas of the brain. The kind of coherence you might see reflected in things like the 40 Hz gamma waves, which are often linked to conscious awareness and focus. This extended macro-scale quantum state is what could potentially provide the unified substrate needed for a single, coherent moral intention to form just before the objective reduction event.
Which brings us smack into the biggest wall these theories always hit. Decoherence. The brain being warm, wet, and noisy. It should just destroy any quantum state instantly, shouldn't it? That's the standard argument.
Absolutely. This is the critical vulnerability. We have to tackle it directly. The main obstacle, theoretically and experimentally, is environmental decoherence. The famous critique, often linked to Max Tegmark, is that the brain is essentially a warm soup, a classical thermal bath. Any delicate quantum superposition needed for thought should just vanish instantly.
And instantly means really, really fast, like femtoseconds.
Exactly. Classical calculations often put decoherence times for anything complex in the brain down in the femtosecond range. That's 10-15 seconds. But conscious processes, decision-making, happen over milliseconds, even seconds. There's this huge mismatch in timescales. Orders of magnitude. That's why many critics just dismiss these quantum brain ideas outright. The thermal noise, they argue, should just collapse everything back to classical immediately.
Okay, but ORCH, OR, and QEH proponents must have a counter to this, otherwise the whole thing's dead on arrival. How do they get around the decoherence problem?
Well, they mounted a pretty strong counter-argument. They pointed out that many early critiques perhaps oversimplified the brain's environment. They argue that if you factor in specific biological details, like how tubulin proteins polarize and change shape, how charges move, The high dielectric constant of the water nearby, it changes the picture significantly.
Right, the brain isn't just a passive bucket of warm water. It's highly structured. There's insulation, compartmentalization.
Exactly. And when you redo the calculations, including these factors, the suggestion is that decoherence times could be extended quite a bit, maybe into the millisecond range, perhaps even longer under certain conditions. Now, that still doesn't automatically guarantee consciousness lasting for seconds, but it does make the initial idea much more plausible. It suggests quantum effects could persist long enough to potentially influence rapid cognitive events like forming an intention.
Okay, so maybe it's not femtoseconds, maybe it's milliseconds. But you still need to hold that moral intention state long enough to actually make the conscious choice. Milliseconds might not be enough for complex deliberation. How do they explain maintaining the state?
This is where they introduce a really crucial concept: active coherence maintenance. The argument is the brain isn't just passively succumbing to decoherence. It's an active system, burning energy specifically to maintain quantum order. The analogy is often made to things like lasers or certain quantum technologies that manage to maintain coherence even at room temperature. It takes energy, constant input.
Wait a minute. If maintaining this quantum coherence for, say, a difficult moral choice takes metabolic energy, doesn't that kind of imply that being good is literally more costly biologically? That seems almost too neat, a bit convenient for the theory.
That's a really sharp and important question, and QEH addresses it directly. The proposal is that the energy needed comes from highly ordered water molecules around the microtubules, a process powered by nearby mitochondria. So this links the abstract idea of committing to an ethical action directly to concrete, measurable cell biology, bioenergetics.
So the actual cost of making a moral choice could be physically quantifiable at the cellular level.
Precisely. The idea is that committing to a complex, high-coherence moral choice, maybe a selfless act that goes against basic survival instincts, requires maintaining this very fragile, highly ordered quantum state just before the collapse. And that requires a measurable burst of metabolic energy to actively fight off decoherence during those critical moments. So QEH argues the effective decoherence time isn't fixed, it's dynamic. It depends on your cognitive state, your emotional state, and crucially, the depth and complexity of the moral intention itself. A simple choice might need less maintenance. A really tough ethical commitment takes real measurable energy.
Wow, that connection is,
That's real.
profound. Linking mitochondria and cell respiration directly to moral strength. Okay, this theory is definitely high risk, but you can see the revolutionary potential if any part holds up. We need to see how they plan to actually test this. Moving from theory to experiments, it sounds like they need a multi-pronged approach, starting with phase I correlation.
Phase I is all about looking for the signal, establishing if there's even a hint of non-classical activity related to morality. The goal is to see if they can detect non-classical patterns of synchronization when two people interact around a moral task. These are dyadic interactions, two people.
Yeah.
And the method they propose is using high-density EEG and MEG hyperscanning.
Hyperscanning. So recording both brains at the same time while they interact or solve something together. What kind of test?
Exactly. They'd put pairs of subjects into tasks involving complex moral decisions. Things like scenarios requiring altruistic sacrifice versus self-gain, especially where their choices are linked or need to be coordinated. Now, people have done classical hyperscanning studies before, looking at standard things like brainwave power in certain frequency bands, and typically those studies show differences between the subjects, reflecting, the individual cognitive struggle, just two classical brains working independently.
Right. But QEH needs more than that. It needs evidence that the two brains somehow acted as a single, coupled quantum system, at least briefly, while they were grappling with that shared ethical problem.
Precisely. And that means shifting from classical analysis tools to quantum ones. To really test QEH, the source says they need advanced techniques from quantum information theory. For instance, applying things like coherence criteria based on partial transposition, or methods designed for measurement-based quantum coherence.
Okay, let's slow down there. Partial transposition. That sounds pretty technical. It's usually used in physics labs, right? To prove entanglement between photons or qubits. How on earth do you apply that to messy EEG data from two brains?
It is highly technical, yes. But essentially, it's a mathematical test designed specifically to detect non-separability entanglement. The idea is, if you measure correlations between the brain signals of person A and person B, and those correlations are stronger than any possible classical explanation could allow, meaning they're not just communicating classically or influenced by the same environment, then partial transposition is a mathematical tool to certify that their joint state must be entangled. If they can compute what's called a negative partial transpose from the coherence data derived from the hyperscans, that's considered strong mathematical evidence for non-classical correlation.
And if they find that entanglement, what does that suggest about the shared moral intention they were forming?
The ultimate goal here is to find a violation of classical limits, something akin to violating a Bell-like inequality, which is the gold standard for proving quantum non-locality in physics. Detecting non-commutative quantum measurements between the branes would be the key signature they need to certify non-classical coherence. Non-commutative just means certain pairs of properties can't be perfectly known at the same time, a purely quantum effect. The rationale is really profound. If they share moral intention, maybe that collapses their joint quantum state towards a shared ethical outcome. It would suggest their neural quantum fields became entangled, especially during that intense moment of forming a synchronized moral commitment.
Okay, so phase I is looking for the signature, the hint that something non-classical might be going on. But correlation, even really weird quantum correlation, isn't causation. That's the old saying. They need to show a causal link. Which brings us to phase II, trying to establish that link through, wow, molecular manipulation.
Yes, this is where the engineering side really starts to ramp up. Phase II aims to leverage a known mechanism from quantum biology. It's called the radical pair mechanism, or RPM. RPM describes the quantum behaviors, specifically the electron and nuclear spins of certain transient molecules called radical pairs. These are molecules that briefly have two unpaired electrons.
Can you simplify RPM a bit? How does it work in the body?
Okay, think of these unpaired electrons like tiny spinning magnets or compass needles within molecules in the brain. When two of these magnets are briefly paired up in a molecule, their relative spin states, whether they spin together, a singlet state, or opposite, a triplet state, turn out to be incredibly sensitive to external magnetic fields, even very weak ones. And crucially, the RPM effect works even with magnetic field energies much smaller than the background thermal noise. That's why it's plausible in a warm biological setting. This mechanism is already the leading explanation for how birds navigate using Earth's magnetic field avian magnetoreception. And there's evidence it also influences things like nerve cell growth and microtubule assembly.
So the idea is to use the body's own built-in quantum sensitivity to try and influence a moral decision, like using this molecular compass to gently steer someone's ethics.
That's basically the principle behind what they call quantum steering. The experiment would involve subjects doing moral tasks, maybe versions of the dictator game, where they choose between being fair or selfish under carefully controlled magnetic conditions. Condition 1, just the normal Earth's magnetic field as a baseline. Condition 2, inside a special room shielded from almost all magnetic fields, a hypomagnetic environment. And condition 3, the crucial one, exposing them to very weak, oscillating magnetic fields. And these fields would be precisely tuned to known resonance frequencies of these radical pairs.
Why ultra-weak and oscillating at a specific frequency? Why not just blast them with a strong magnet?
Because a strong magnetic field would likely just cause classical effects, overwhelming the delicate quantum process. RPM relies on the coherent manipulation of the spin state. You need a very specific low-energy nudge that resonates only with the quantum dynamics of those radical pairs. By tuning the oscillation frequency of the weak field to match the natural wobble frequency of the electron spins, it's called the Larmor frequency, you can effectively encourage the radical pair to flip from, say, a singlet state to a triplet state, or vice versa. And since the singlet and triplet states lead to different downstream chemical reactions, you could potentially influence subsequent neural processes.
And the causal prediction here, if QEH is right, what should happen to their moral choices?
If the hypothesis holds, then subtly tweaking this intrinsic quantum process, the spin coherence of molecules involved in intention formation, should provide causal evidence. The outcome they'd measure is the bias in moral decisions. If they can reproducibly influence choices, say, make people slightly more altruistic in the dictator game by applying weak fields tuned only to those specific RPM frequencies, that would be strong evidence. It would suggest they've managed to quantum steer moral choice.
Okay, moving from correlation to actual causation like that would be huge, transformative. But the ultimate proof, you'd think, has to involve getting right down to the hypothesized hardware, the microtubules themselves. That sounds like phase 3, precision quantum state perturbation.
Exactly. Phase 3 is definitely the most technically demanding and maybe the most critical step. It moves from broad magnetic fields affecting the whole system down to the cellular level. The goal here is to directly target and modulate the quantum activity within the proposed substrate, the neural microtubules. And the tool they propose for this is using next-generation bioluminescent optogenetic markers.
Optogenetics. Okay, normally that involves using light to switch neurons on or off, classically, right? You insert a gene, the neuron becomes light sensitive, and zap, you control its firing. How are these quantum markers different?
They're engineered for a much more subtle, non-classical job. The proposed marker system needs to do two things, ideally at the quantum level: perturbation and sensing. For perturbation, the idea is to use a very specific light pulse tuned to activate the marker to essentially scramble or disrupt the quantum processes happening within the microtubule lattice itself.
So the light pulse acts like a targeted, localized anesthetic almost, messing with the quantum computation.
That's a really good analogy, actually. General anesthetics, interestingly, are known to bind to tubulin proteins in microtubules, and one theory, linked to OR, is that they work precisely by disrupting this quantum coherence. So this marker would aim to do something similar, but with the precision of light, and crucially designed to affect the quantum state without necessarily causing the neuron to fire a classical action potential or release neurotransmitters wholesale.
Okay, and the sensing part. How do you actually see or measure the quantum state without destroying it?
That's where the bioluminescent aspect comes in. It would ideally provide a way to visualize the activity non-destructively, in real time. Combined with some advanced detection methods, the source mentions using things called coherence witnesses, it could potentially allow researchers to assess whether the microtubule lattice nearby is actually operating in a coherent quantum state. A coherence witness is basically a measurable quantity that gives statistical evidence for quantum coherence. It helps confirm you're really looking at a quantum process as it happens.
So the absolute key test here, the real make-or-break moment for QEH, according to this, is achieving a clear dissociation, separating the quantum effects from the classical neural firing. That's needed to rule out simpler explanations.
Absolutely essential. If standard optogenetics just changes firing rates, and that changes behavior, that's classical neuroscience. The QEH test has to show that manipulating the quantum layer independently affects deep conscious intent. So the experiment has to, say, disrupt the microtubule coherence using that light pulse, while confirming that the classical nerve signals monitored simultaneously with maybe EEG or direct electrodes remain largely unchanged.
So you're looking for a scenario where a person's brain activity looks pretty normal. Classically, their EEG, fMRI, action potentials are all within range, but they suddenly show a measurable problem with complex moral reasoning or commitment. They become inconsistent, maybe can't finalize a difficult ethical choice.
Yes, exactly. Yeah. If you observe that kind of deficit or inconsistency in their ability to form and hold a complex moral intention while their basic classical neural transmission seems fine, that would be incredibly powerful evidence. It would strongly suggest that a non-computable quantum process, separate from the standard firing patterns, is fundamental to ethical choice. That's the critical and incredibly difficult distinction they need to demonstrate to really validate QEH over conventional views.
If, and it's a huge if, but if these three phases were somehow successful, spanning correlation, causation, and direct cellular manipulation, the philosophical impact would be just immediate, total.
Oh, it would necessitate a complete rewrite of our understanding of reality. Confirming QEH, confirming that our intentional moral choices physically participate in wavefunction collapse, would force physics itself to adapt. It would mean morality isn't just a human construct or a biological adaptation, but an irreducible fundamental feature of the physical universe. Subjective experience and objective reality would kind of merge.
It completely demolishes that historical wall between the physical sciences and ethics, even spirituality maybe. It would radically alter how we think about free will, about personal responsibility. It would suggest ethical decisions are cosmic events woven into the very fabric of reality.
Absolutely. If the universe itself is inherently responsive to our moral choices, if our decisions are actual objective reduction events collapsing reality into one state versus another, that redefines responsibility entirely. It implies free will isn't some illusion cooked up by our neurons, but a real, physically demanding, non-computable process that's actually essential to how the observable world comes to be.
Speaking of responsibility, though, phase 2, the idea of being able to quantum steer moral choice, that sounds incredibly dangerous. The source rightly flags the monumental societal consequences. Mandatory oversight is stressed.
It's a massive ethical consideration, an existential risk, potentially. If you could actually statistically bias human ethical decisions using tuned magnetic fields, that knowledge itself is a profound societal threat. The source is clear. Rigorous, integrated ethical and social review isn't optional. It's mandatory from day one. And not just bioethicists, but sociologists, political scientists, people who can think through the potential misuses.
Yeah, the worry is obvious. If weak magnetic fields, precisely tuned, can subtly nudge people towards being more selfish or more altruistic, that's a recipe for manipulation or coercion on a scale we can barely imagine. Governmental scale, even.
Without a doubt. Specific safeguards would be needed to ensure the technology and the knowledge gained couldn't be weaponized or used for coercive purposes by governments or other powerful actors. Any research consortium working on this would need incredibly strict controls and transparency protocols.
Now, a project this wildly ambitious, it spans fundamental physics, cutting-edge quantum information science, complex biology, neuroscience. It's going to need very special funding, right? Way beyond a typical university grant.
Oh yes, it demands high risk, probably multi-agency funding that bridges these normally separate fields. The three phases, though, are mapped out strategically to align with different kinds of funding bodies, based on their risk appetite and specific goals. It provides clear deliverables at each stage.
So phase one, the correlation and theory part, that's more foundational.
That's about validating those novel coherence metrics, applying things like partial transposition to brain data. That kind of high-risk fundamental theory and cognitive science work often aligns with bodies like the National Science Foundation, NSF, or private foundations interested in big questions, like the Templeton Foundation is mentioned.
Okay. Then phase two, the molecular spin control, that shifts more towards tech development and applied quantum biology.
Right. And that phase needs groups specializing in demonstrating causal links between behavior and specific quantum manipulations like the spin control. Given the goal of demonstrating actual cognitive modulation and the potential national security implications, this phase targets agencies focused on technology development and perhaps defense research. The source mentions the European Research Council, ERC synergy grants, and pointedly, DARPA in the U.S.
And finally, phase three, cellular manipulation that needs serious bioengineering muscle.
That's the bleeding edge, prototyping those next-gen bioluminescent optogenetic quantum markers for fiddling with microtubules directly. That kind of super high-risk, potentially transformative biological engineering fits the profile for things like the NIH Director's Pioneer Award program.
Yeah.
So the whole QEH program is envisioned as this structured, potentially global effort to figure out if consciousness and ethics are truly fundamental physical properties, confirming the reality and significance of human moral choice.
This whole deep dive really forces us to ask that fundamental question again. What is a moral choice? Are we just incredibly complex biological machines running fancy cultural software? Or is the act of choosing itself physics in action, literally shaping the reality we inhabit?
And if we take the core premise seriously for a moment, that our ethical choices actively participate in collapsing the quantum wave function, then the universe isn't just a backdrop, it's responding to our morality. It suggests consciousness and ethics aren't just afterthoughts, but active co-creators of what's real. So what does it truly mean for the world to be, as the source puts it, an entangled layer, where our ethical intentions and physical reality are inseparable? Where your freely chosen moral action might be the ultimate expression of physical law. That's the cosmic scale of choice QEH leaves us thinking about.